recording. So let's go. Chapter 3.7 Abstract Data Types. So today we're going to cover 3.7, 8, 9, and that's it because 3.10 is our exercises.
Yeah, we're not doing those.
So 3.7 Abstract Data Types. A data type, or simply a type, is a set of values together with a set of operations on these values. So I think we've seen this before, and um, that's okay enough, I would say.
Uh, I would be able to nitpick about foundations, but let's not do that.
Wow, I think it's the perfect time to do that.
Uh, well, most of my objections would be about the whole thing with infinite sets, because, well,
Uh-huh.
yeah, I just don't feel like it, I guess.
That's
uh,
wise choice. Um, and we're gonna go the ML route of making having an ADT as abstract data type. And by abstract, we mean that the type is completely defined by its set of operations regardless of the implementation. So this is pretty reminiscent of how you implement types in ML languages.
using, well, technically ML has both, right? If you use the module system, you can see modules as being abstract types.
We're gonna go there today.
And if you use the thing that it calls a type, those are actually algebraic data types like Haskell style, right? Where you have pairs and sums. Well, not pairs,
I think, well, maybe I'm
products and
mistaken,
sum types.
but I think they say abstract data types for those things as well in the ML things that I read at least.
They shouldn't, because those are defined by their structure,
I even
not
I
by their
even I even
operations.
think we saw that in the first session of Karuta, like a year ago, when we were looking at some slides from of some professor of from some university. ADTs were presented for types as well, not only modules. I think I even remember that. And I even told you that. Like, hey man, we have like a overloading on this terminology now because ADT can
Well,
mean abstract data types and algebraic data types.
it's unfortunate that those two names have the same abbreviation because those are two different concepts, right? They shouldn't be mixed together.
Well, the only thing I'm gonna say is that I never seen in any sort of ML source material algebraic data types being mentioned. That's everything I'm gonna say because I don't know,
Yeah,
I
that's
haven't read the books and the the
if
French
that's
books,
the
I guess.
case. Yeah, no, if that's the case, that's definitely a mistake because, well, normal types in ML are algebraic, not abstract, because they are defined by their structure, not by the operations you do on them, right?
Yeah, I agree with your take, by the way. I'm just saying that I never seen that terminology being used in ML source material, but maybe I'm wrong. Maybe I don't know, in the original French books of ML, they actually have that mentioned in there. Anyway, we're gonna go see some examples. So we have a declarative stack. So this we are trying to define. Well, we're trying to define a stack type based on some properties and some APIs. So we have some laws, some laws are like constraints that we are expected our type to obey. So these are pretty intuitive. I don't think that's problematic. And then there's this thing, and actually I want to talk about it. So attentive readers will notice an unusual aspect of the definitions. Pop is written using a functional syntax, but one of its arguments is an output. So can we talk? What is it calling a functional syntax in this case?
Well, it's defined using fun and it returns a value, right? So it's an expression.
So that's what it's called, the functional syntax,
Well, yes, use it as if you would call a function and it returns the stack without the elements that you are popping, right?
which returns a true out. Well, we could have written in this way, which by the way, this is how we did it in Karate recently, right? We originally had pop as how can I say? Usually Previously we did the pop that returns only the stack, and now we are doing the version that returns the stack and the popped element. Writing pop SE is an example of programming with a functional look, which uses functional syntax for operations that are not necessarily mathematical functions. We consider that this is justified for programs that have a clear directionality in the flow of data. I don't know, how do you feel about this? Like, because this is kind of saying that it's not functional. It's not functional, this version, and the other one
That
is
no, no,
functional.
that version is functional because it has one output, right? That's kind of the point. The other version is pop SE, but it is an output argument. It's a second output besides the return, well, the quote unquote return value, right?
Ah, okay, so that's why it's talking about mathematical functions, and I got confused. It's because this thing has two outputs, and they are two outputs. You're not a single tuple.
Yes.
Okay, now I see the difference. Now I see the difference. I made a confusion there. It can be interesting to highlight this directionality even if the program is not functional. In some cases, it can make the program more concise and more readable. Um, For the stack, the function look lets us highlight the symmetry between push and pop. It makes it clear syntactically that both operations take a stack and return a stack. Then, for example, the output of pop can be immediately passed as input to push without needing an intermediate case statement. But this is not the case, right? In this version here, you can't just pass the output of this pop to the push because this returns a tuple.
Yes, that is correct.
Yeah. Yeah, so this comment is kind of weird because
No, no, it's because the definition that gives above, the official quote unquote definition, is in fact like you call
this
pop
one.
SE, you can directly put the return value as an argument to push. That works just fine.
Oh, it's because in this case we are doing a bind on the E, but the output is actually S1, which is the
Yeah,
stack
which
in
is a
this
stack.
case. Yeah, I keep forgetting that we have data flow variables. This means that having multiple outputs doesn't remove the ability to pipe like to compose functions. You can have
Yeah.
many outputs, but that doesn't forbid you from composing.
Yep.
I keep forgetting that. That okay. A declarative dictionary. So now we're gonna make a dictionary. So we have dictionary operations. Then we're gonna have an example of a list-based implementation. Then we have go to a tree-based implementation. Nothing too fancy. There's nothing here that I think it's like new. This is just doing like again. This is using data flow variables and stuff like
Yeah, it's
that.
just putting together stuff that we already know.
Exactly. And then we have a state-based implementation, which we're gonna see again. We have many foreshadowings of this thing about explicit state in this chapter. We are very far away from it, but apparently you can have amortized constant time, which is what we talked about last time about having very infrequently doing costly operations. So that's what the amortized means.
Right, because I'm pretty sure the state-based implementation, and this is well more foreshadowing, I guess. I'm pretty sure the state-based implementation uses a hash table, which needs to be periodically resized, right? That's why it's amortized, and not
Mhm.
worst case.
Mhm. Then we're going to make a program that counts the frequency of words in a particular piece of text, and this is pretty important. We're going to use this throughout to the end of chapter 3. And then we have a couple of auxiliary functions, such as a function to identify a valid character. We have some transformation functions, incrementing the frequency functions, and then this is the main body of the thing, which is essentially like counting the words and also removing the capitalization of them. Then we
Right,
also
because we
have
don't want to. Yeah, don't want to count capitalized and non-capitalized variants of the same word as different words, right?
well, actually, I lied. This is the one that is creating the words, and this is the one doing the counting. And then this is the one that you're gonna call. And yes, what you said is right. Yeah, so then there's an explanation of what these functions do, and then we have an example, which is the word and a tuple, or a list of tuples in which the first member of the tuple is the word, and the second member of the tuple is the frequency. Yeah, I shouldn't say frequency. I should say appearances. Um, so, and then we have an example using like a meta example. So if you pick this program written in this book, applying the book itself as an input. So this is like a Quine example. I'm joking. I'm joking.
Well,
I know
it's
this is not a Quine, but it's just funny.
and it cleverly avoids the infinite recursion problem by using the function on an early draft of the book, so a
Exactly.
previous version, not the current one.
Yeah. And then you can run that. And then we have a comparison of the execution times of using different implementations, keeping the same API. And with this, it's horrendous. It's like 5 minutes. With ordered binary trees, we have a speed up process, and using explicit state, we have an even faster time.
Yep.
Nothing too crazy. Like this is expected. Um, so yeah, and then we go to secure abstract data types, which is the first new thing to me about these session that we're gonna discuss.
Yeah, I've seen this a few times before reading this book because I studied a little bit of the E language that it mentions.
Yeah, it mentions the E language.
And I've seen actually John Schutz's kernel actually has the same idea of sealer and unsealer pairs as part of the language definition. If you ever read his work, I shared it in the server before. Although I will admit that it is a bit niche because it's about Lisp and specifically about Fexpers, which are not really part of the mainstream, even within the Lisp tradition. So
Yeah. Yeah, so what are we talking about? Because what you just said is a bunch of gibberish because we haven't talked about it yet. I understood what you said, but I'm just for the recording purposes. What are we talking about? We're talking about uh, having cracks in your type implementation, and then somebody can exploit these cracks. And what do we mean by crack? We mean these bullet points. So the program is much harder to maintain. For example, say we want to improve the efficiency of the dictionary by replacing the list-based implementation by a tree-based. You have to score the whole program to find out which parts depend on a list-based implementation, because you can exploit the fact that you know the internals of your type and you know it's a list, so you may be using, for example, length on it because you know it will work given its internal implementation. But if you want to change it, now you have a grep problem, right? You have to grep all the use cases for it to identify, okay, this is actually relying on the fact that the programmer knew at the time that this is a list-based implementation.
yeah. Actually, one thing we can say, I guess, this chapter doesn't really use that word, but it's actually about encapsulation. The whole buzzword in OO, it actually means something, and this chapter tells us what it is.
No, but we saw encapsulation before, right? We saw in chapter 1.
Well, yes, that was basically just using procedures because you can't look at the internals of a procedure, right?
No, 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 no. That's chapter 2, I think. What I'm talking about chapter 1 is when it was defining the buzzwords like object and class and stuff, and then adding the requirements and like evolving the Digimon to go all the way to a class. One of these words that makes the evolution is up encapsulation. We've seen that word before.
Oh, right, that is true, actually.
Yeah, but you are right. This is talking. This is talking on the realm in the realms of encapsulation. You're right. There is also a problem of error confinement. This word was changed. Interesting. They changed from error confinement to fault confinement.
You mean in the physical version of the
Yeah,
book?
yeah.
I see.
If the program has bugs in one part, then it can spill over into the abstract data types, making them buggy as well, which then contaminates other parts of the program.
Yeah, this is basically okay, you are handling the internals of your type directly, but there's a bug in your logic that does not use the actual interface of the type and that messes things up for other people.
Yeah, essentially you are instead of using what the API is providing you, you make it one yourself. And then if you have a problem there that's not relying on the
Yeah,
internal
if the
implementation.
API, yeah, if the API relies on a certain invariant that you are breaking, then it's gonna mess things up. It just will, you know.
The program is susceptible to malicious interference. The more subtle, this is a more subtle problem that has to do with security. It does not occur with programs written by people who trust each other. This happens with open programs. An open program is one that can interact with other programs that are only known at runtime. So what are we talking about? Well, we are talking about either a dynamic linked library or we are talking about a .o file, for example.
Or we could also use eval, I guess, in languages that have that.
That's true. You can also, we're talking about evolve. What if the other program is malicious and wants to disrupt the execution of the open program? Because of the evolution of the internet, the proportion of open programs is increasing.
I guess this also counts if you want to include that JavaScript in a browser, right? Because you are downloading codes that you then execute.
Yeah, yeah. You have to put a lot of extra security checks when you're downloading stuff from the internet. Um, so the basic, how do we solve this? The basic idea is to protect the internal representation of abstract data types values, the stack values, from unauthorized interference. The value to be protected is put inside a protection boundary. And there are two ways to use this boundary, which are very confusing in my opinion. We have the stationary
Uh,
value. The value never leaves the boundary. A well-defined set of operations can enter the boundary to calculate with the value. The result of the calculation stays inside the boundary. So this is like what we've been doing
uh,
until now.
Not really. This is more like this doesn't really work very well with the declarative model, which is why we go straight to the second point in the implementation examples. But like if you have a mutable object that's inside of a boundary, of a protection boundary, as it calls it, you could make some operation that reads the value, does some computation, and then mutates it without ever pulling it out of the protection boundary, you know?
We've seen this before. That's what I'm talking about. We've seen an example before talking about lexical scoping that does exactly what you said, but the cell is unmutable. It's just a reference, like a label.
Uh, well, I guess that counts.
And we're gonna see this again in the example below when we talk about the keys and the names. So I don't really understand why we are not going through this point first, because as far as the text goes, aren't we already doing that using lexical scoping?
We aren't really because we're not actually putting the result of the calculation inside of the boundary. We're returning it, right?
That's true. That I can agree with. But what is it? But the text doesn't talk about that.
Well, the text says the result of the calculation stays inside of the boundary, which is not the case until now. Actually, it won't be the case until we see mutable state, I guess.
I have a hard time buying this one because to me, if you have the difference lists, for example, and I don't give you an API to bind the tail yourself, like how is that different than saying that the result of the calculation stays within the inside the boundary? I see. I kind of understand what you
No,
mean,
no,
which is that
there's
the mutable cell is still contained within those walls, right? You cannot get out of those walls.
actually the different lists we saw until now, they were not encapsulated at all.
Oh, they were.
Like
We
anyone,
we seen an F function that does exactly that in the previous chapter. Do you remember the
um,
function that was talking about persistent data structures? That was a function that was on purpose binding the tail, that allowing you to not have the slightly mutability problem that we talked about. That then does making the data structures completely independent, right? That's what I'm talking about. You are making
oh, you mean
operations.
you mean
That,
the one where it was doing basically a copy of a list, right, to avoid
exactly.
the issue?
Exactly. So let's say just for the sake of my argument that I don't allow you to have access to the direct data structure of the different lists with a tuple. I just give you an API. And then that API would give you a copy function or clone function or whatever that would do exactly what that persistent data structure section was talking about. And that would be entering the boundary to calculate with the value. That's fine. But I agree that I'm, when you return from it, the result is not being kept inside the boundary in some sense of the word, right?
Right. I guess the second point we will see in the examples later, but the idea of well, the second point actually says explicitly at the end, right? The idea with the difference list, you would have to do something like, okay, I pull the value out of the boundary, I duplicate the list, duplicate the unbound variable, so there are now two of them and they are independent, right?
Mm-hmm. Mm-hmm.
The key point is that before returning, in order to maintain your API secure, you would have to put them back inside of the boundary, right? Which is what the second point is all about.
Yes. Yes. No, but that's kind of that's kind of the thing. I think I'm starting to understand more clearly the difference in comparison to when I read this first. In the stationary value case, the value never left,
Yeah,
but in
this is
the
only
second
doable
case,
if
it did.
yeah, the first case is not really doable yet because they don't have explicit state in the model
I,
at this
I
point.
agree. I agree that you can only never ever leave if you have mutable stuff. And then we have the mobile value, which is that the value can leave and re-enter the boundary. When it is outside, operations can be done. Operations with proper authorization can take the value out of the boundary and calculate with it. The result is put back inside the boundary. Yeah, so from from a user's point of view, I think these two approaches are kind of transparent because as we're about to see, we're gonna make a type later. Like, let's actually go there just for me to make sense. Yeah, when you define your type, I'm just gonna call pop and push. I have no clue this is being protected at all. So if you're using a mutable state or you're using this thing, I can't tell from just calling point of view. So
You can tell if you try to share the same values in the same value in
no, no, no. But that's
like you
trying to
try,
break it, right?
no no
That's
no
not.
if you
That's
try
doing
to
more
use
than
the
just calling it.
no no no, it could be just calling it like if you take a value, stack in this case, right? And you try to push something, and then you try to push something else onto the same stack, um, whether it's mutable or not will be observable, right?
No, no, no. But you are doing at least two operations there. That's already different than what I said. What I said is if I do a push, and this is the API, and I grab the result, and if I do another single push, but you're using the explicit state version, only with a single push each, I can't see the difference. Only if you do what you said, which is you do two pushes.
Yeah,
That's correct, right? Because well, if you do two pushes, how can you observe the difference? If you don't pick the output stack of this and do a push again and see the result of that, right?
you have to use pop afterwards, and then if you
Exactly.
try to yeah, if you try to pop more than once, if it's immutable, it's gonna fail because you
Exactly.
pushed
Only
values
one.
onto two different stacks. Well, they
Exactly.
are logically different, right?
Exactly. Exactly. But you are doing more than a single operation. You're doing at least two operations there. What I meant is if I do this push or I do the other push, which looks exactly the same, both are ducks and they both walk like ducks,
Yeah, you
essentially.
wouldn't be able to tell if you just call it once.
Exactly. So that's what I meant by being these two approaches being transparent from the user's point of view. But Marinho is right. If you try to break it, if you try to make a test to see the difference, you can, and you will observe the difference. Um, well, we're gonna see first the second approach, which is the mobile value, and apparently later we're gonna see the stationary value, which again for shadowing, we're gonna see that with explicit state. And then we're gonna. This is actually something new to me, right? Because I never seen this approach done before. So how does
It's
this
very
work?
nice. It's very nice.
How does this work? Um, you need to provide the key to enter the boundary and manipulate the value, essentially. And when I read this the first time, I was heavily confused because I was like, wait a moment. I'm gonna, when I create my type, it's gonna give me the type and a key, and I'm gonna have to keep this key hanging around and passing to my functions and everything. That sounds annoying as fuck.
Lexical scoping to the rescue.
Yeah, and then it came the cheating, which is actually you don't have the key. The lexical scoping has the key, and we are exploiting that fact so you don't have to pass that, like, you don't have the inconvenience of having to have the key yourself.
Actually, you shouldn't have the key because then you can break the encapsulation, right? You can just open up the value,
Yeah, but I
which
am the
is
owner of it, and I don't have the key. That's kind of weird. I was the one that
no,
created the type.
no. But the point is that someone else may use the type, right? And you don't want to give them the key.
No, exactly. Like I have the burden. I have the responsibility of keeping the key protected. But you are not allowing me to even have a chance. That's what I'm talking about. Like the Lex, like you know you don't trust yourself, so you put that hidden even from you. We're gonna see
That's
that in a
true
moment.
that's like encapsulation in the truest sense. Like even you can't break the
Even
encapsulation.
yourself, you can't break it. The authorization we need to enter the protection bar is called the key or a name, and I think this is a very bad naming for this. But okay. And then apparently, this is when you generalize this idea, you actually go to something called a capability, which is another
Yeah, cap-
weird word choice.
yeah, capability-based security is there's a whole area of research about it. It actually mentions this later.
Yeah, we will go there. So the declarative model defined so far does not let us do that. We need to extend the model. We need two extensions: one to protect values and one to protect unbound variables. And then this table shows the resulting kernel language with these neutral operations. So we are introducing these things.
Yep.
Um, and then we're going to achieve this with this effect with a particular, well, a particular implementations of wrapping and unwrapping mechanisms. So um, one way to make value secure is by adding a wrapping operation with a key. That is, the internal representation is put inside a data structure that is inaccessible except to those who know a special value, the key. Knowing the key allows to create new wrappings and to look inside existing wrappings made with the same key. We're gonna call this basic type a name. And a name is a constant like an atom, except it has much more restricted set of operations. In particular, names that you can print names, so like it's real secure. Nobody can even look at it. You have to read the bits of the transistors. Um, and then these are the two operations that we can do with names. We can get a new one, and you can compare them.
Yep.
Um, and this is not declarative because new name doesn't return the same output every time. Probably because this is doing some mutable monotonic stuff under the hood.
Yeah.
The guarantee of uniqueness means a new name has some internal memory, as I said before. And then we have an example. So we have this list. How can we make it secure? We create a key. And then this is what bothered me. Like, okay, who is holding this shit? Somebody needs to hold this shit. And then you have a function that receives a key, compares k with the key. Okay, so this is the first foreshadowing. SS has scope access to key.
Yeah.
Otherwise, this if will not be able to be here.
Yep.
Uh, so that's something. We say that it wraps the value S inside SS. If one knows the key, then accessing S with SS is easy. Just provide the key. We say this unwraps the value S from SS if one does not know the key. Unwrapping is impossible. And then, yeah, this is where the lexical scoping comes, because you are making a procedure called new wrapper that returns you a wrap function and an unwrap function, and the key is completely hidden inside the body of this procedure.
Yep.
So And take a look on the bodies of these two functions. We're not returning the key,
We
which
aren't.
means that when you instantiate new wrapper, the caller of it, you yourself doesn't even know what is the
What the
key,
key is.
what the key
Yeah.
is, and that is why it's not annoying. That's how they managed to not make it annoying.
Yeah, the point is kind of that you don't really need to know. You just need to have the wrap and unwrap and know that they are paired. You don't care about the actual underlying key. You only care about it insofar as it makes the thing work.
No, I understand that in terms of usefulness is very okay, but in terms of the intuition of what is a secret key, uh, it's only in the domain space that we find this idea of like, okay, I have a gigantic hash function, a gigantic hash that is my master password of everything else. You don't know the hash yourself. You just care that it's useful because it has some invariants. That's fine. But in terms of the intuition of having like a password, like if you're not a tech person, you know your password.
Yeah, that's not how this works.
That's definitely not how this works. Like this is not 100% not how this is going to go. And then we just use what are these functions doing? Exactly what we just said, right? This is doing wrap and unwrapping, passing the key to it, and the key that is only knowable within this lexical scope. So this is more examples of how that works, and this is a pictorial representation of how this works. So you have a protected value, and then you do your operation. Ideally, your operation in your ADT will have already the wrapping and unwrapping mechanisms baked in. So it will look like this. So
Yep,
the wraps and unwraps are happening, and you have no idea they are happening at all. Um, and then this is how it looks like. So you unwrap it, so it leaves the protection boundary. You do the operation, and then you repackage it, right? And then you have it back, which is already protected. So
yep.
this is the implementation of the stack using that stuff. Nothing too crazy. And then we have the unbound variables problem, which is a perfect example. Would be the difference lists.
Right,
Be,
if you're going to use that as a queue and you want to be able to, okay, if you want to be able to securely export the contents of the queue so someone else can read them, but you don't want to allow them to bind them,
bind them.
yeah, we need a mechanism for that.
And then the way that this is done, and I think this is a criticism for the book. I should have explored an example because we're extending the store. There are no examples of this. It's just saying. I would prefer an example step by step when we're doing the compilation chapter 2, a step by step process of a full example having the two stores interacting with each other. Because the way
I
we're gonna
think
do
we
this,
act- I think you'll actually see this in details in one of the appendices, but yeah, it's not in the main text of the book.
yeah. So so this is a read-only variable, right? Return a read-only view of x, and this is being done by double exclamation mark. Um, so yeah. Um, I need to sniff. One moment, please. I'm back. So this is how we're gonna do it. We're gonna have a read-only view that will using extra syntax, and we're gonna read-only view sit in a new store called read-only store. And if we try to bind suspense, whatever that means. This is not clear. Are we gonna raise an exception? Maybe.
It's going to wait until somebody else binds it before continuing.
Ah, okay. Creating fresh names. And then we have the centralized approach. These also reminded me of certificates, HTTPS.
Certificates are technically, well, I suppose they would be technically the decentralized approach because they use cryptography to generate random data and then
Yeah,
generate
but
keys and all that.
it's
But
not that decentralized.
yeah, no, because for certificates as they are commonly used, you actually have you have a list of people who you trust to
Yeah.
generate those, and in that sense, it is centralized. Yes.
Yeah. So it is. I think that matters more than the fact that it is encrypted, by the way, because it means that we have to have a selected, curated list of entities that we can trust to do our stuff, regardless if it's encrypted or not. But yes, in here it's written that the decentralized approach usually comes with encryption, like enforced encryption. Um, but well, this is just about the name creation. And then we have a secure declarative dictionary. So the same thing, but with dictionaries as we did with stacks. And
Yep.
then, yeah, this is talking about more the capabilities of the security thing that Marinho mentioned before. Um, yeah, it's beyond the scope of this book. And yeah, but this is important. We consider only a small part of the vast discipline of security, namely the programming language viewpoint. We need security mechanisms, and we will discuss that. And one of them, surprisingly, lexicoscoping, because the lexicoscoping doesn't give you the access to the key. And languages that have these mechanisms, we're going to call them secure languages, and that's pretty important to to have. But I think I don't know if you agree, but my impression is that the industry tends to prefer the safe languages instead of secure languages. If you know what I mean. They don't mean the same
Yeah.
thing at all.
Yeah. No, they don't. Like.
Safe languages have the semantics of allowing your program to handle resources in a safe manner. This is talking about having your program barricaded against malicious intent from the outside.
Yeah. Basically. Yeah. There's a difference. Like people usually say safe language as a shorthand for memory safe language, right?
Exactly.
Where you can't
Exactly.
fumble the memory management. But yeah, that doesn't really extend to full-blown security, right?
Exactly. And then we have capabilities. So the protection is introduced to make secure abstract data types is a special case of a capability. Uh, there is a definition here. Yeah, a capability is an unforgeable language entity that gives it its owner the right to perform a given set of actions. Um, and why is the declarative model insufficient to go to the full extent of capabilities? Because of two reasons. Um,
Well, one
where
of them is immutability, unfortunately.
one of them, yeah. So there is a session here.
It's later. It's actually later. It's after this whole principle of least privilege.
Yes, yes, that's
Hello,
true.
Willie.
Hello, Uli. That's true. But let's continue here. By unforgeable, we mean that it is impossible for an implementation, even one that is intimately connected to the hardware architecture, such as one in a similar language, to create a capability. You cannot forge it, so it's like you can be sure. Um, an owner of a language entity is in any program fragment that references that entity. For example, yeah, in a sense, you already have this with records, that's true, and procedures for that matter. Um,
Yep.
an unbound variable gives its owner the ability to bind it, a read-only variable gives its owner the ability to read it. Um, so yeah, so in a such a sense, we've seen this before, right?
Yeah, this is just trying to say, hey, we can actually use these things for security, you
Yeah,
know?
yeah, external references that a procedure is using. This is also something that you can talk about capabilities. But then you go to the principle of least privilege, which is each entity should be given the least authority that is necessary for it to get its job done. The
Yeah,
recent example we have of that was on Friday, when Marinho and I were discussing about should we put this in a let or not. And Marinho said something very close to this.
yeah.
uh, determining exactly what is the least authority is in all cases an undecidable problem. This is just another version of the halting problem. But we can get we can get some stuff done using approximations of those things. Uh, for example, an entity can be given the authority to create a file with a given name and maximum size in a given directory. For file, cursor granularities are usually enough, such as the authority to create a file in a given directory. Capabilities can handle both defined and coarse grained cases easily.
Oh yeah,
Uh,
here's the point.
yeah, so this is why the declarative model, the declarative capabilities, they are insufficient.
You
It's
can't revoke them.
and you cannot change, yeah, you cannot revoke or add them over time. And for that, we need the explicit state again. So again, a lot of foreshadowing. I don't know why, but this book I loves doing foreshadowing of explicit state. And I noticed this since chapter one. It loves to say, okay, we're gonna get there, we're gonna get there. And then we have non-declarative needs. So this is talking about the impure necessity that we have. It's the same meme as always. The box gets hot, but there's no output.
Yeah.
It's the same thing over and over again. So what are we going to be doing? We're going to be doing files and we're going to be doing I/O. So text input and output. Well, and why are they not declarative? Because they don't respect the constraint that the same inputs for the same function call will give you the same outputs.
Right, because if you try to read a file with a name at different points in time, you may have different contents there depending on the state of your hard drive.
Exactly. They are not mathematical, and they are not. They don't have this invariant guaranteed. So that's why they are non-declarative, and we need them because that's how we. Because the word is impure. That's it. Uh, okay, so we're gonna talk about that, and this is actually also introducing the idea of modules. We're gonna talk about them later in 3.9 as well. But for now, I'll just go over these ones. So this is essentially, man, this is defining what a file is and what a text file is. Like, come on, you're stupid, but not that stupid.
I mean, the whole book is trying to be precise, right? So I guess this checks out.
Well, I agree, but I don't know. I have a feeling we could have all of these in a glossary somewhere, and this is all like assuming that you know those things. But that's okay. I guess this is because I already know what those things are. But then the book says that it's not trying to teach you, like newcomers, and it's talking about what a text file is. Come on. And then we have a file, and then this is how you load a module in, I guess, in the repo in this case. So this is how you do that, and this is how you read a file. Shown. And apparently, well, this is a dynamic language. They are exploiting the fact that this is a dynamic language, and you can pass the file path in multiple ways. So there's this way, there's this way.
By the
Um,
way, this whole thing about virtual strings is it's basically an explicit way of doing ropes, which is something I mentioned recently.
I
It's
saw that.
basically a way, yeah, it's basically a way to do concatenation efficiently at the expense of being able to read efficiently. But if you're just going to use the string to dump the content into the disk or open a file, it doesn't really matter that much. That
Yeah,
reading it can become inefficient over time.
yeah. And then we have writing a file, so you can open a file, write some stuff, and close it. We have an example of that using the for loop linguistic abstraction. And then we have GUI. Yeah, so this is man, this is kind of weird because it has the property that, at least from my knowledge, is usually correlated to immediate UI. So there is some point here that it says that if you click on it, but you release and the pointer is outside of the area, it will not register it. Uh, and I've seen that in when people talking about immediate UI, but the way that you construct the UI is OOP all the way, in a particular sense.
This actually is very reminiscent of HTML.
No, it is HTML. Well, it reminds me of HTML, XML, but the fact, and I think it talks about them being objects somewhere. Yeah, here.
Yeah, we.
The user interface is specified as an nested record supplemented with objects and procedures. So then we go all the way. So you are basically creating your widgets, and the way that they look in code kind of looks how they're gonna look in the UI as well. So for example, there is a very big example somewhere. Yeah, this one. So you're saying that there's this, and inside there's this, and this, and this, right? And you specify how they are gonna be glued together.
Yeah, that's important for resizing.
That's important for resizing. But anyway, it is HTML, XML, uh, and
Like,
like at least how you write it, right? Like spatially looks like something that when you look at it, the way that it uh, looks kind of reminiscent of what's gonna appear on the screen. So you have to
yeah.
pass them like, oh, this is inside that, and this is inside that. So it's gonna look like that in the code as well. It's not gonna look perfectly aligned because of the gluing rules. So for example, how this button is just on top of the other one. It's not on the side like it's in here. But that's because of how the gluing works.
On top of the other one. No, it's because of the label of the record, right?
Because of the label of the record.
Yeah, because there's TD, which is top down, which is you're vertically
Yes,
stacking things, and there's
vertical
LR, which is
stacking.
which is left to right. You're basically putting things side by side, right?
No, yeah, but that's what I'm trying to say. When you're writing something in here, they may spatially not look exactly like what's going to look like on the final product. That's what I meant to say.
Yeah, yeah, that's fair.
And then we have the gluing rules. That matter for the resizing, as Manning already said. More examples of building that. And then there is some, yeah, I was really confused about this in and out thing. But there's an explanation here saying that the in gets the text from the first text widget and binds it to X, and then you can get that X on the other widget. So this is basically a message passing in a way,
Uh,
I
kind,
guess.
kinda. Yeah, because you're declaring in and out. You're binding them to the handles of the text widgets, right?
Mm-hmm.
And then you're basically saying, okay, I'm going to I'm going to get the text from here and send it over there by using this X variable in the procedure A1. Yeah, your cursor is right over. Oh, wait, that's my cursor. No, it's yours. Yeah, it's right over it
Yeah, it
basically.
is. Yeah. No. Yeah. And then we have stateless I/O data I/O with files. So this, yeah, it would be a great help to the programmer if it would be able, if be possible to save any value to a file and to load it back later. This reminded me of Racket Tower, right? Because the way that we did this was
Yeah, we were just saving
Racket
Racket
code.
code as data. Yeah,
It's funny that it doesn't show us how the file looks like. But I wonder if they're doing the same shit.
it's probably some kind of binary encoding for the basic data types. I'm guessing. Um, if they wanted to be efficient, right, in terms of space usage.
Yeah,
So it wouldn't be exactly human readable if they did it using a binary format.
yeah. And then we have this program fragment, and we want to save all these list of things in the fact file, and then we want to load them back. Yeah. And then I have a question about this because this is talking about how data flow variables makes it possible to use a variable before binding it, because it's saying that these two programs will output the same thing, right?
Right.
How does this work on this version though? Because in my understanding, this is going to be waiting. This is only a single thread, so this will be waiting for browse F1. It will not reach this.
I'm pretty sure that each line that you input in the interactive interface, like each time you hit enter, that spawns a separate thread.
Ah, that's not written in here.
I think it's mentioned way at the beginning of the book, but
Oh, okay,
Like
maybe I forgot. That's possible. But I was kind of weird.
it's
Wait, aren't these gonna just block forever? Like, what are we talking about?
yeah, if they did, the interactive input would become unusable until the previous expression returned, right? That's not ideal from a user experience perspective.
No, yeah, no. From a REPL like perspective, that's fine. But I completely forgot that fact that this is actually spawning a separate thread. That's why this can
Yeah,
continue.
no, yeah, no, but you are right. If you actually put this in a file and try to run the file, that's gonna block.
Yeah. We emphasize that the loaded value is exactly the same as the one that was saved. There is no difference at all between them. This is true for all possible values. And there we go. And then there is more examples. If you save it and load and stuff like that. The first case creates and reads the file. The second one does not. The first case raises an exception if there's a problem in creating or reading the file.
Yeah, basically it's saying, yeah, if you just put the save and the load in the same program, that's equivalent to having them in separate programs. And then if you just remove that, the only difference is you're not accessing the file system anymore.
Yeah. And then we go to the final section of this session, which is 3.9, program design in the small. These two paragraphs, they are kind of weird in a sense because it's trying to make a distinction between programming the small and programming in the large. We'll call the resulting programs small programs and the other and large programs respectively. The distinction has nothing to do with the program size, but rather with how many people are involved in its development. When I read this, I was kind of like shocked because this is essentially saying that if I wrote a program for a decade, but only by myself, this is a small program. And I was like, okay, that's kind of weird. But then there was a gotcha here. So small programs are written by one person over a short period of time. Large programs are written by more than one person or over a long period of time. The same person now and 1 year from now should be considered as two people. So that's how it gets out of this gotcha that I had.
Yeah.
Because I'm like, okay, and then there is design methodology. So this is engineering. For the folks not initiated, this is what we do or rather we should be doing as engineers. We have an informal specification conversation in the beginning. So we start by writing down as precise as we can what the program should do, what its inputs and outputs are, and how the outputs relate to the inputs. And this is not formal because we're not using mathematical notation or any laws, by that matter. Replacing the syntax with fancy Greek symbols do not make it mathematical. Um, uh, the properties, the invariants, and the laws are what make them mathematical.
Yeah.
Then you have examples, specifically contrary examples to make this, trying to break it, usually.
Yep.
And then we do some exploration. So to find out is to well, we explore using a REPL. Thank you very much. Thank you very much.
Yeah, even if your language doesn't support a REPL, you can just make a small program using a thing that you want to explore and just run it like separately, right? But
Yeah.
yeah, REPL makes this way easier.
And then we do it, right? So we do it and then we code it. We make a rough outline of the operations needed to calculate outputs from the inputs. We then fill in the blanks by writing the actual program code. So this is actually the main bulk of the work. The operation should be simple. Each operation should do just one thing. To improve the structure, we can group related operations in modules. And then we do tests and reasoning about it. Another criticism, this doesn't mention property tests at all.
Well, it doesn't mention the kinds of tests you're going to write, right? It just says you should test it.
No, but it mentions the kinds of tests a little bit, including the examples we came up before, right? So it's kind of
Wow.
talking about at least some kind of tests, but there are no mention at all about property tests. We correct errors until the program works well. We can reason about the program its complexity using the formal semantics. Testing and reasoning are complementary. It is important to do both to get a high quality program. I was expecting to have at least a sentence in here. Like, we tried out a series of test cases, including the examples we came up with before. It's interesting as well to introduce property tests, and there is a footnote with something here.
That's fair.
This book is like I was expecting, given what the book so far, that it would at least mention that in here.
When did property testing become popular, though?
It has Haskell in here. It doesn't like. What are we talking about? It knows
Yeah,
Haskell.
but when did quick check become a thing? Is the question.
Oh, I guess. I have no idea the answer to that question, but I don't know. Um, Theorem solvers, proof assistants. Did they become popular?
That's fair.
Because that's what they are all about. Quick check is just the popularization, or making property tests a commodity. That's what quick check did, as far as I know. But the whole idea of proof assistants are about this. So, yeah, commodity really, in the sense that it popularizes, so the vast majority of the users in that domain can now use it as well. So it becomes cheaper, more popular, people talk more about it. So you can see, for example, quick checking in all sorts as inspiration for the languages, such as Erlang, I think Elixir as well, Glean, I think what was
Closure.
the Closure, Java. So like essentially, quick check is the iPhone of the smartphones, but for property testing. So it's kind of in that sense that I meant commodity in there. These steps are not meant to be obligatory, but rather to serve as inspirations. Feel free to adapt them to your own circumstances. For example, when imagining examples, it can be clear that the specification has to be changed. Yeah, there is some sort of back and forth between testing. Well, these three, you kind of go back and forth between them depending on the results of the reasoning and testing. And then we have an example of this methodology being applied. So we have the same problem as before. We want to count words in a text file. So we have an informal specification, which is usually written in English. And then we have some problems that these specifications are covering, such as what we do about emojis. What about UTF-8? What about what is a word? That's a great point. What the fuck is that?
Yeah.
And then we have to go back and refine it. So we refine it a little bit more. And we go with the final word as this. And then we're gonna ignore emojis for now. And then we notice that we can reuse the implementation from the dictionary from before. And then it mentions that we can use string to atom to convert character strings to atoms.
Yeah, because the dictionary we had was indexed by atoms, not strings, right?
Exactly. Well, this is not mentioned, but we are also getting rid of the capitalization. We should have mentioned that in the specification. Um,
Right.
and then we go from there. And then we go from there. To this, we added a code to read the file and display the output in a window. For this, we use the file operations and graphical user interface operations of section 3.8. It is important to package the application cleanly as a software component, as explained in the next two sessions. And then we finally go to the buzzword software component, uh, which is going to be a way that you're going to organize our program. So it starts by defining a separation between logical units, which is the interface and the implementation. Only the interface is visible from outside the logical unit. A logical unit may use others as part of its implementation. And then this is where we going to go to modules, which I don't know. Is it fair to say that this is like 95% of ML modules?
Yeah, it's just leaving out the static typing of them, right?
Well, I wouldn't say the static typing by itself, but the how can I say this?
I guess most of the examples here are also not explicitly parameterized.
Exactly,
Uh,
exactly. Well, it is kind of parameterized when we introduce the import. But as far as I can tell, that somehow ML does that. ML, the import is not about the module, but the interface of the module. So when you do
Yeah.
an import, you're not importing everything. You're just importing what is the module exposing. And
Well,
that's
you are
not,
also not.
go on.
Well, this in this the this module doesn't have to expose everything, right? Either.
Well, yes, but I feel that in the code that is not explicit, but in the text it kind of is. There is a, well, I'm skipping a lot of stuff. Let's go back. But in some place here it is written that it's
No,
an
no, no.
interface-based functor.
No, no, yeah, right there. You see, basically the functor down there is going to desugar to a procedure like that in this page actually. Yeah, and you can just make functions that are not part of the export. That's a thing you can do.
Well, I guess that's fair. There's no example of that. Oh, actually, there is this.
Yeah, merge sort is not part of the exports in this case.
Yeah, yeah, yeah. The only reason that I said 95% was because the import kind of gave me the feeling that, okay, are we talking only about the interface in this case? But I think you're right. It mentioned this in this example here, and I just missed it. The merge sort. Cool. So let's actually go back because there's more I want to talk about. So yeah, we are here. Okay, so how are we going to do that? We're going to do that via a module. A module is a part of a program that groups together related operations into an entity that has an interface and an implementation. So the interface is a record that groups together related language entities. And an implementation is
Usually,
a set of language entities that are accessible by the interface operations but hidden from the outside. Go.
yeah, and it mentions usually you export procedures, but you can put anything in the interface, right?
You can put anything in the interface. Um, a module specification is sometimes called a software component. And this is overloaded,
Yeah.
of course. So we're going to
Yep.
call it functor. Because why not?
Be- because ML basically.
A functor is a function whose arguments are the modules it needs and whose result is a new module. To be precise, the functor takes the module interface's arguments, creates a new module, and returns that module's interface. Yeah, so this is what I was talking about being written somewhere. We need more parts to make the functor work, which is the import, the export, and the define. So the
Which is
import,
basic.
go on.
Yeah, the import is what I depend on, the export is what I provide, and define is okay, here's how I'm actually implemented, basically.
Yeah, we're going to use a linguistic abstraction to make it. So we're going to see shortly how that translates. In the terminology of software engineering, a software component is a unit of independent deployment, a unit of third-party development, and has no persistent state. So, header-only libraries, DLLs, at least some DLLs. And I don't know if all of them are independent. Maybe not all of them. But usually header-only libraries, DLLs, stuff like that. Functors satisfy this definition and are therefore a kind of software component. With this terminology, a module is a component instance. It is a result of installing a functor in a particular module environment. The module environment consists of a set of modules, each of which may have an execution state. And in Mozart's system, by the way, functors are the compilation units, which is interesting.
Yep.
The system has support for handling functors in files, both are source code and object code. Source code can be compiled or translated into object code. This makes it easy to use functors to exchange software between developers. An application standalone, it can be run without the interactive interface. It consists of a main functor, which is evaluated even when the program starts. It imports the module it needs, which causes the other functors to be evaluated. The main functor is used for its effect of starting the application, and not for its resulting module, which is silently ignored. Evaluating a functor happens in three steps. First, the module's needs are identified. Second, the initialization code is executed. Third, the module is loaded the first time it is needed during execution. So it's only when needed, let's say executed. This technique is called dynamic linking as opposed to static linking, in which the modules are loaded when execution starts. Well, yeah, so they work like DLLs. Cool.
Basically, yeah.
Let's say an example. So we have our my list. I'm exposing, well, I'm creating those things and I'm exposing those things. And the way that's gonna, well, this is how it's gonna desugar the functor syntax.
Technically, the version before was just writing the thing, the instantiation in line. This one is packaging it function, and this function
Yes,
happens to be the desugaring of the syntax we will see later. I think it's in the next page, right?
yes, Marinho is right. So this is defining it. This is wrapping that in a function. Using procedure abstraction, we can turn this module into a software component. This software component is a function that returns a module. So it returns a module. Each time mylist functor is called, it creates and returns another mylist module. And it could have arguments, which are the other modules needed for mylist. So again, this is very heavily ML inspired. From this definition, it is
Yep.
clear that functors are just values in the language. They share the following properties. A functor definition can be evaluated at runtime, can have external references to other language entities, can be stored in a file by using the pickle module. This can be read later. It's lightweight, can be it can be used to encapsulate a single entity, just as one object or class. And then we have, yeah, this part is interesting. A software component can be built that implements component-based programming, in which components determine at runtime which components they need and when to link them. Okay. Even more flexibility is possible when dynamic typing is used. A component can link an arbitrary component at runtime by installing any functors and calling them according to their needs. And this is the linguistic support we're going to provide to it. So this is gonna how the functor is going to look like. Yeah, so this is where I find it confusing. Where is the in the example here that I need as a like my input?
Well,
That's
well, well, in this case, this module has no other dependencies, right?
no, yes. And I guess yeah, that's how you define that, right?
Yeah.
But yeah, this example is just like an example that doesn't need imports. Then the module can be created as follows in interactive interface. So this is how you call it in the REPL. It takes a list of functors, links them together, and returns a corresponding list of modules. And then you have importing modules because again, a functor should be yeah, but that's the thing. This is a functor that doesn't take inputs. Should this be called a functor? That's
Well, in ML, because of the static typing, this would just be a module, right? Because of, well, it takes the idea of currying to the module level as well, so there's no functor with no arguments, basically.
exactly. So that was what was bothering me. That's the problem. Because if you have no input, are you a functor? In here you are, but in ML you're not.
Yeah, structure is a nullary functor. I guess that's one way to look at it.
I agree with Uli that a structure can be seen as a nullary functor. Uh, okay, but well, if you have imports, you can do that as well. Um, to import a library module is enough to give the name of its functor. So this is how it looks like. And then, well, this is using the full count line, so you need to import that, and so on and so forth. Yeah, this particular functor is defined for its effect, not for the module that it creates. It therefore does not export any interface. So this is doing an effect, right?
Yeah, basically
Uh,
you're gonna load it and it's going to display the number of,
exactly.
well, technically that would be the number of users, right? If you look at
Yes,
the
yes,
file that it's reading and counting the lines.
yes. And then we have an example of a standalone program, and we're going to use everything that we have done before to make this happen. So you're defining a functor. Oh, actually, that's also a good thing. A good question. How do we define the name of the functor? Is this file
You
based again?
you don't. It's anonymous, right?
Yeah. So in here, the functors they are all anonymous.
It's when you import the functor, you bind it to a name then, you know?
That's another difference from ML. right? Because like in Okemo at least, a file is a module, but you can have other modules and other functors with other names. They are not tied to a name to the file like not only to the file. You can give them names, separate names. Like for example, in Karuta we did the make, right? There's our
Right,
functor is called make.
right.
Um, the functors here they have no names.
Yeah, they are anonymous, of course.
But how do you call them then?
Well, you're typically going to load them from a file, right?
Oh, so they need to be tied to a file. You can have
Well,
anonymous
you can
modules
have
inside ML, I'm pretty sure. No. Okay. Go on, man.
well, you can have a module inside of another module, and you can have both of them in the same file, right? They are just nested. Then,
No, but what if they are not nested? What if they are just in the same file? Can you
what
do
if they
that?
are just in the same file? I think with the way Pico works, you can't put more than one value per file unless it's a list.
That's so sad. Okay, I'm very disappointed right now. Okay. So this is a functor that will export to you these things, and these are the implementations that well, we're not gonna have access to them. This is another functor that now requires these other two modules.
I mean, it kind of makes sense because if the functor is the unit of compilation, you don't really typically compile multiple dynamic libraries into a single file, right?
But aren't modules? Oh wait, in here the functors are the units of compilation. In ML maybe they are the modules, right? So maybe a
Yeah.
functor is this sugar to something else. Okay. Well, maybe I'm saying bullshit. Okay, I don't know how Chemo compiler works. Um. Anyway, so here we have all the functions we have seen before. Nothing too crazy about that. And this is this is the body of the program.
This is the body of the program, essentially, yeah.
Wait a moment. You can have a body of the program in the middle of a functor?
Now, in the body of the functor, in the define, you can have side effects, which will happen when it's loaded, right?
Can you do that in
And for
ML?
I don't see. Oh, actually, probably can you? Can you have just arbitrary statements in the body of a module in ML? I
I
don't know off
never
the
tried.
top of my head. Only says no.
Okay. So that's also another difference. And this is the dependency tree, well, the component dependency tree, I should say. Uh, so this is how it looks. Well, this is how it looks, right? So this is well, the arrows mean that the one
A imports
pointing,
B, yeah.
yeah, exactly. Uh, okay, wait a moment. People are talking to me.
Uli
Okay.
says only place you can have side effects is top level definitions. But isn't a file a module? So a top level definition would be part of the body of a module, logically, no?
Yeah, we should try that at some point. Okay, I'm back.
Yeah, but it's a specific kind of module in standard ML anyways. Yeah, we never actually dived very deeply into the nitty-gritty of
Yeah.
how the module system is used by the runtime, right?
Yeah, well, we didn't. Um, 3.36 shows the dependencies. The Qt component is a multi-system standard library. Blah blah blah.
And here it gives an example of extending the system to show the counts in two different orders, right?
Yeah. Um, no, my bad. People are talking to me and I need to respond to them.
All right.
Okay. Okay, there we go. This is how the program looks like.
Yeah, this is an extension to display 2 frames instead of one. The actual program is in the figures, right?
The actual program. Oh, you're talking about this program. Yeah,
Yeah, this one.
yeah, this program is fine. This application can easily be extended in many ways. For example, the window display can be replaced by the following. So we change it, we do different stuff, we do sorting. Yeah, this is spatial frames, one in alphabetical order and another one in order of decreasing word frequency. Yeah, so this is just extending the previous program. And this is how we can make the. It's a difference between compiling. Yeah, it's different in compilation strategy, I guess. Any function can be compiled to make a singular program. In that case, no export part is necessary, and initialization part defines the program's effect. Given the functor, the compiled functor is created using this command. The standalone executable is created when running following this command. So this we are compiling this functor, right? And this is
Yeah,
we are uh,
compiling of the functor into an executable. I guess X stands for executable in this case.
exactly. And then we have library modules, right? So yeah, this is the very chicken and an egg problem. If you want your language to be popular, you need it to have the libraries. But in order to
But
to convince people to make libraries for it,
it needs
usually
to be
it
popular.
needs to be popular. So, like, I don't understand. The solution to this problem is clearly somebody just needs to do it.
Have you guys actually worked on a NOS project yet? Not
No,
yet, Uli.
no, not yet. Well, yeah, this is basically just saying that you, well, for example, you can make an effort to when you're dispatching your language, your compiler, you also dispatch a set of useful libraries, right? So I don't know, Jai is the first one that comes to my mind that is modern that does that. Zig as well does that. There's a lot of functionality that comes with the compiler. Not necessarily maybe it's gonna be baked into the compiler, or it's gonna be baked like as artifacts that comes with the compiler in a bundle.
Yeah, Z actually bundles the source code of the standard library together with the compiler.
Oh, so
Other languages have
it is
different.
bundled.
Yeah, other languages may have different approaches, right?
No, no, no. But when I say bundle, I mean like physically. So when you again using Jai as an example, when you download Jai, you receive a zip that has .jai files.
Yeah, Zig does the same thing.
But I thought when you have the Zig compiler and you do const std, there are no Zig files like. Oh, maybe in the installation of the compiler, there's where the Zig files are.
Yeah, it's in the installation actually. Because here's the thing.
I see.
The the basic idea is okay. We have a standard library, but we don't really want to pre-compile it because people may run the compiler on different processors, which may have different features, right?
Yeah.
And a big thing about Zig is being able to do easy cross compilation. So it's like, okay, what if we ship the source code and then the library can be optimized for the particular machine that you are actually running with all the instructions that it has available, even if they may not be very common, right? In older machines.
Yeah. Yeah. So in this case, Jai and Zig are doing the same thing. Uh, the importance of libraries is becoming increasingly important. Well, this is like tautological. People understand that. And then finally, library modules in Mozart, which is essentially saying that we have the system modules and the base modules. So the base, they are kind of like built in. So the number, list, record operations in the chapters are base modules. The system modules, they are not available immediately upon startup, which means that you're going to have to import them.
Yeah, they come with the compiler, but they are not in the standard environment, I guess.
Uh, that is also true for Zig and Jai, right? You have to do const std and import
Yeah, you
basic.
have yeah. In Zig, you have the built-in language features, but then if you want to use a standard library, you have to import it explicitly.
Yeah. In Jai, that's basic. Like they use the C style, so it's hashtag import space quotes double quotes basic. That's how you do that in Jai. Uh, the system modules are not available. They provide additional functionality such as file I/O, graphical user interfaces, distributed programming. That's really nice. It's actually very nice that it comes with logic and constraint, distributed logic and constraint programming. That's pretty huge. Um, in the interactive OZ menu, open the compiler panel and click on the environment tab. This shows all the defined variables in the global environment, including the modules. Okay, we finished chapter 3. So next time, we're
Declarative concurrency.
going to talk about declarative concurrency. I'm going to finish the recording now.